I have the tremendous honor of welcoming our very special guest presenter to the stage to close out day one of the summit. He is this year's Henry Tremere Lifetime Award honoree. Please join me in welcoming. It's been a long day, guys. Join me in welcoming longtime advocate for patients with experience as a clinician, a nonprofit advocacy leader, a bioethicist, an attorney, a biotech executive, and an investor, and an esteemed author, Dr. Philip Reilly.
Okay, great. I'm just going to wait for 1 second because I'm delighted to see so many people moving in here at the left, but there's many seats over here. I feel like I'm going to have to look this way only, which will be hard. So, okay. So hello, everyone. I feel really honored not only to be an awardee this year, but just to have the chance to talk with you who care so deeply about the same things I care about. When I was in my hotel room earlier, I was looking at some of the material that Global Genes presented, and I was really struck by the message on the cover: learn, connect, inspire. Well, I'm here to learn from you, both during the talk and afterward. I definitely want to connect with you, and I really want to inspire you, which is hard because you're already inspired or you wouldn't be here. So let me tell you what I'm going to do in the next 40 minutes. I'm going to deliver to you a very real message of hope, not a false message of hope, but a very real one. And I'm going to build an argument based on what I've seen in my own lifetime about what can happen in a relatively short period of time when inspired scientists and parents work together. So I'm going to tell you some stories. I don't have a slide presentation. I really do not like to use them. I like to engage with you. But before I tell my first story about phenylketonuria, I want to say on a very personal note a few words about what brought me into this space. As a physician in the 80s and early 90s, I was the director of a large institution in Massachusetts that housed, and I'm using that word housed for a reason, about 1,000 persons with, in those days, what was called mental retardation. It was a very sad place to work. It was literally a backwater, only 10 miles from the gleaming hospitals of Cambridge and Boston, a late 19th century set of red brick buildings with hopelessly ill patients getting almost no attention. I was really there in charge of their custodial care. And it was I can still remember the moment where I decided to change my life about 16 years ago. It was one day when as the chief doctor of the institution, I would occasionally drop in on the buildings and check out the patients. And one hot afternoon, I went up to a small facility and looked in, and there was a single young woman there of about 30, obviously very mentally retarded, and rocking herself all alone in her underwear. Room smelled of urine. There were no pictures on the walls. It was plastic furniture. And I felt absolutely ashamed of the world in which I lived. And that's when I left what I was doing to try what was really, at the time for me, a really very daring move to see if I could, in some small way, become a part of an effort to develop new therapies for rare disorders. And that's been the story of my life for the last 16 years. But I'm really not here to talk about myself. I'm here to talk about a selected few of the many heroes that I have either known personally or have known about. So mindful of the short time we have together, I'm going to try and tell you about 4 or 5 stories, and I'm just going to show you pictures of individuals. So I'm going to begin with the story about phenylketonuria. Affects 1 in about 10,000 people. And today, many people think of it as a success story. Kids with PKU do quite well. So why is that? Well, my first hero that I want to talk about is a young woman, about 32, in Norway in the early 30s, who had 2 children who had severe developmental delay. And her name was Borny Egeland, and she went to doctor after doctor everyone gave her the usual message, there's nothing you can do, go home and take care of your children. Until she met a man to my far left here, Ivar Asbjørn Følling, who happened to have been trained in nutrition as well as medicine. And he decided to take a chance on working with her. So he examined her 2 children, and he did all the kind of biochemical tests he knew at the time. And he was an intelligent man. He kept working with it, and he noticed a musty odor in the child's urine. So he said, there's probably a biochemical thing going on here that I don't know about. I could talk to you for an hour about Asbjørn Følling, and you would fall in love with the man. So I'll only talk about him for 2 or 3 minutes. I've already mentioned the young woman who helped him get started. He, by trial and error, found out that a certain chemical called ferric chloride would change the urine of certain people with mental retardation from yellow to dark green. And that led him to infer the biochemical pathway, and that was a 4-decade journey that ended with the success we have had in recent times. So Følling asked to go around to different institutions in Denmark to see if he could, Norway rather, to see if he could test the urine of many people in institutions. And lo and behold, over and over again, not in large numbers, in small numbers, he found patients whose urine turned green. And so he realized it was he inferred it was an autosomal recessive form of mental retardation. Then there's an interruption because of World War II. And the story starts over again in the late 40s when a German pediatrician working in England had the idea, well, if the child can't metabolize phenylalanine, one of the amino acids, let's just give the child a lot less phenylalanine. Pretty obvious now, but not then. And lo and behold, although no one was able to diagnose the children early enough to make a big difference, he did a very interesting experiment. I want to tell you about this experiment because a lot of times now we hear the story N of 1. I'm sure you've heard that phrase. For very rare disorders, let's just go with an N of 1. This was the first N of 1 story that I'm going to tell you. So Bickel, the German pediatrician, said to a woman who had a little boy or girl with mental retardation, we can't cure the mental retardation, but let's put the child on a very low phenylalanine diet and see if the child gets better in any way. Mom came back, it's hard to do, by the way, especially then. Mom came back a few months later and said, my child has a greater sense of engagement with the world and is definitely much less cranky. She smiles more. This was a tremendous victory at the time for the mother. I mean, the child was extremely irritable all the time. But here's the N of 1. Very brave for both the mom and the doctor. Let's put the child back on a normal, meaning high phenylalanine diet. Couldn't do that with NIH funding today. And what happened? The child got a lot worse. So the N of 1, that's the beautiful thing about monogenic disorders. You can learn a great deal from an N of 1. Not everything, of course. And this sort of built the argument about a low phenylalanine diet. And then in the 50s, Mead Johnson became the first company to develop a commercially available low phenylalanine diet called Lofenac. But this problem was still we weren't getting the kids early enough. Thus my, if I could go back to that slide with the 2 people on it, can we go back? How do I do that? This way, there. Thus the story becomes Robert Guthrie's story. Robert Guthrie is another hero. His work took place from about 60 to 68. He was a academic oncologist, trained at the University of Minnesota, 6 kids, loved to sail. His second child was born and became mentally retarded. And then he had a nephew who developed PKU. And he said, we have got to screen every child at birth so we identify them really early and we can put them on a low diet right away. This is food as therapy. And I don't have the time to tell you the whole story because if I do, I won't tell you the other great stories. But anyway, Guthrie, in the space of a couple years, developed a special kind of assay that could identify high levels of phenylalanine in a newborn infant's blood in a matter of about 72 hours. He then, in a series of studies, proved that if you put these kids immediately on a special diet, they did much better than if they weren't treated. Then he switched hats. And in 6 years, from 1962 to 1968, he convinced every legislature in the United States, because public health law is state-based, to enact a compulsory newborn screening program from PKU. So that by the time I was a doctor at the Fernald State School in Waltham, we had done so well with treating kids early with PKU that the medical residents from Harvard would come out to see me so they could visit with a patient who had never benefited from the diet. There were two young women I took care of who never were screened and therefore was severely retarded. So the point is, in 1932, when the lady in Norway approached Dr. Følling, to 1972, it took 40 years, but kids today in the United States and the West, born with PKU, live a normal life. They have a diet that you would rather not be on, and we can do something about that. We've had a tremendous victory. It's not a total cure. So there's an example of hope fulfilled. Følling is interesting because he was a kind of a retiring guy, and when President Kennedy decided to give somebody an award for service in the global service of mental retardation, one of his assistants sent Følling a letter asking him to come to Washington. Følling didn't even believe the letter was true and wouldn't come until finally somebody flew over there from the Kennedy administration to say, no, we really want you to come and have a party for you in Washington. So that's a story. 40 years, PKU, a complete mystery, unknown, to when I would talk to a mom or dad about a child with PKU, I would give a great degree of confidence in speaking with them about the diagnosis. So this is not an isolated story. There are many stories like this. I can only tell you about 4. Here's another one of my heroes, David Weatherall, still alive, probably one of the greatest hematologists in the Western world. His story begins when he was a young pediatrician in Singapore, just after World War II, doing his 2 years of compulsory service. Didn't know anything about the disease I'm going to talk about, but he had a lot of time in his hands, and an Asian military man, a sergeant or something, in the group he was working with, brought his daughter to see Dr. Weatherall. And his daughter had a disease that we now call beta thalassemia. Some of you have heard of it. Some of you may know people with it. That's a disease where the children do not make enough normal hemoglobin. Now, it was Weatherall, over the space of about 20 years, who actually really dissected the molecular aspects of that disease and ultimately came up with an approach to it that was a beginning approach that then got refined, and that was to figure out a way, especially since this is a disease that mostly affects Asians, not just Asia, but mostly in Asia, that if you could figure out a way to give very low-cost blood transfusions on a periodic basis, you could keep these kids alive. Now, as is the story with many genetic disorders, that was only a partial solution. And some of you know why. If you give repeated blood transfusions to somebody, you overload their iron stores. Now, you sitting there, the average person in this room has a total of 5 grams of iron in the body. 5 grams of iron is a third of a teaspoonful in your whole body, and iron's in most of your cells. If you get blood transfusions regularly, in the space of a year or two, you quadruple the amount of iron in your body. So we were saving the kids, Weatherall was saving the kids from blood transfusion, but they were all getting iron overload. And they're actually dying from iron storage disorders, really, because it would affect the heart, the pancreas, and the like. So the next part of the story, and I don't have a slide for it, was the development, and this is in the 80s, of chelation therapy, molecules that grab iron and take it out of the body. And this became very important. It has led to the state where a situation where today in Europe, in the United States, a kid born with beta thalassemia, you can tell their parents that this kid is going to do very well into his 40s, 50s, maybe 60s. And we don't, the nice thing about these stories is we don't have an upper age expectation for life expectancy anymore. They just keep living longer and longer. And then we learn more about the disease in different ways. But with iron chelation therapy, we still haven't solved the problem of beta thalassemia that, by the way, rare in the US, affects millions of people in the world. I'm fond of telling audiences, it's another autosomal recessive disorder, that there are more carriers of beta thalassemia in Asia than there are people in Great Britain. So while it's a rare disease here, it's a public health problem in the Asian world. So how are we going to solve that problem? In the United States or England, somebody born with beta thalassemia today will live for many decades. But as we speak in this hour, some child under the age of 10 will die of beta thalassemia in Africa or Asia. The median life expectancy in most of the world is about 10 to 12 years right now, excluding US and Europe. So it's a victory, but we can never give up, right? We get inspired by our victories and we keep going. The latest, before I go on to Judith Pool, one of my very special heroes, the latest news on beta thalassemia is there's hope. There's hope. It's still early that a gene therapy may offer a kind of solution for this that is long-term. So we just got to keep working on it. Now, Judith Pool. There's a nice picture of Judith. Let me tell you a little bit about her. Too often in medicine, as is of course true in most walks of life, the women don't get the attention they deserve. Judith was a bright young undergraduate at the University of Chicago. She did a PhD there and part of her time there in biochemistry. She was married to somebody who became an English professor. She followed him, an old story. She followed him to a small college in New York, upstate New York. Then she followed him to Stanford. In 1953, they divorced, and she struggled to get an entry level. This is a woman with a PhD from the University of Chicago. Struggled in the 50s to get an entry-level technician position at Stanford, but she got it. Then, working almost alone and with no real funding at all, she attacked a problem that had stumped American and European scientists for decades, and that was the problem of how to take care of people with hemophilia, a disease we have known for 2,000 years. It's written about in ancient texts. By 1900, there were hundreds of papers published on hemophilia, particularly in England, and people knew what was wrong. And how odd it is to call it hemophilia, love of blood. The problem is just the opposite, is the blood's not working right? But people didn't understand the so-called clotting cascade and why these kids would bleed so much. And of course, it became very famous because Queen Victoria's family had this disorder running in it. And, one of the children of the last Tsar of Russia had the disorder. So back to Judith Pool, but now she's working all alone with maybe a couple of young students with her, trying to figure out what is it in normal human blood that keeps people from bleeding out. And she would study it every which way with very primitive tools, and much more sophisticated labs had failed to uncover the story. Until one day she did a very simple experiment. She just began centrifuging blood tubes so they'd be layered by molecular weight, the different components of the blood. And then she would very slowly decant or pour out little bits of what was in the tube, very slowly, maybe 5% at a time. And then she would test with the system she had the amount of that aliquot that would clot. And lo and behold, she found that the very last bottom of the tube, what was essentially sludge, she called it sludge, the heaviest stuff, was loaded with some factor called the AHF, antihemophilic factor, that would really clot blood very effectively. So she named it, she couldn't call it sludge, so she named it cryoprecipitate. Sounds good. And in 1963 and 1964, in a papers in Nature in the New England Journal of Medicine, overnight, back to my message of hope, overnight, she transformed the world of therapy for hemophilia. Prior to that, as there are several wonderful books I talk about in my book that have talked about the journey of being patients before this time. Prior to that, children were managed by blood transfusions, again, that was overloading them, but not just the iron overload, volume overload. If you were a little kid with hemophilia in the 50s, you might spend, and I am not exaggerating, 50 to 100 nights in the hospital because people were trying to titrate the amount of fluid they give you, and they're in danger of turning into having heart failure because of fluid overload. And 4 years later, cryoprecipitate was widely available, and almost overnight, the life expectancy of people with hemophilia tripled in the United States. Again, You're in the wilderness, you're all alone. Think about the diseases that mean the most to you. You're all alone, and then suddenly everything changes. It can happen. I'm going to tell you more stories like it until I get yanked off the stage. What I often do is ask the folks in the back to lock the doors and keep you here until I'm done trying to inspire you. So, but hemophilia, of course, had a tragic period after that, as you may know, because of the problem of HIV infection from pooled donors. There was a time in France and the United States in the 80s where the life expectancy of people with hemophilia that had gone from like 10 to 40 or 50 dropped back to 20. That was a spike. Very sad, fortunately behind us. So this is another theme that a little different from those ones I'm talking about. This is Antonio Cao, who's an Italian physician, also a hematologist. And he took another approach to beta thalassemia, and I mention it not because it's my favorite approach, but because it worked. Because people with sickle cell anemia, who carry sickle cell anemia gene or beta thalassemia gene, are at lower risk for malaria, evolution has driven up the frequency of mutations for those folks. And in Sardinia, where this work was done originally, Greece, Sicily, 1 out of 8 people carries a gene for beta thalassemia. At that level, it's a public health problem. It means 1 out of 64 couples is at risk for having an affected baby. And literally in those areas of the world, there were not funds sufficient to take care of the kids. Cao pioneered carrier screening, not leading to any mandatory behavior, and this has been done for many other diseases now as well, but saying that, look, you should know that if you marry, you have a mutation. If you marry someone else's mutation, you have 1 in 4 risk. In 10 years, the frequency, without utilizing abortion as an alternative, I might add, in 10 years, the number of live births of children in Sardinia with beta thalassemia fell by about 95%, just because of education. Education is another theme at work here at Global Genes, and this is one example of its very powerful impact that it can have. So this is, I could put these slides up all night, but I probably couldn't keep you here. This is kind of the last picture I'm going to show you, and then I'll have a few remarks as I move towards a conclusion, and maybe we'll have time for some questions. So Roscoe Brady, another hero. Roscoe Brady, who's still alive, I believe, in his late 80s, was a Harvard-trained physician, and during the Second World War or Korean War, he got a gig to work in a lab in Washington, and that, an Army lab, and that changed his life, and he became basically a clinical biochemist. And Roscoe, this picture of Roscoe, he's sitting here with a little boy who has a disorder called Gaucher disease, which is one of the 50 lysosomal storage disorders. And in those days, if you had Gaucher disease, by the time if you had classical Gaucher disease, this is in the 50s or 60s or 70s, you would develop a huge liver, a huge spleen. Your legs would become bowed because of the activity inside the bone marrow compartments of the legs. You would develop fractures, you would be profoundly anemic, and you would die of infection if you had the classical version of the disease. Why? Why was the liver big or the spleen big? Because the cells were unable to eliminate something from the lysosome, and the stuff just kept accumulating and accumulating and accumulating. So as each cell got big, each organ got big. I mean, the cells will be 10 or 20 times greater in size than they should be. And so the solution theoretically was simple. Figure out a way to get rid of the junk in the cell. The stuff, there's a missing enzyme, it's not working because of genetic mutation, autosomal recessive. So can we somehow fix that cell? And this is the era of enzyme replacement therapy. I'm so honored that on Saturday I'll get the Henry Tamir Award. Henry Tamir, working with Roscoe Brady, took his research into commercial reality. And what they did working together, actually, when Genzyme was just a tiny biotech company, they decided that they would make glucose cerebrosidase, the missing enzyme, and supply it to the child. Let me just say a word about the gargantuan challenge that a biotech company faced working with Roscoe Brady. Where are you going to get the glucose cerebrosidase? Nobody knew how to make it. So the solution was to harvest it from human placentas. And I'm not exaggerating, you needed over 100,000 human placentas in that era to extract enough glucose cerebrosidase and purify it to give it to one child to treat him. I mean, we're facing some really tough challenges in this room. We all know that. But people meet those challenges and go on to do great things. Roscoe Brady and his colleagues published some wonderful papers in the New England Journal in the, I guess, late 80s it was, and showed that in small groups, we always think about the size of clinical trials. Can we go to the FDA with data on just 10 kids and get something approved? How would we do that? Well, go read the literature on the early efforts to get approval for enzyme replacement therapy. Those were not 500-person studies. Later on, they got larger, but the early studies were 10, 20, 30 kids with different diseases. And by the way, one thing I didn't say here, but which I want to say now, every story I told you is an exemplar of a class of disorders. PKU, there are 20 other inborn errors of metabolism that you can manage better or worse by diet. Gaucher disease, 50 other lysosomal storage diseases. More coming. And we'll find a way to help these people as well. So let's see, what have I told you about? PKU, beta thalassemia, hemophilia, lysosomal storage diseases. All fatal disorders within the lifetime of most of the people in this room. Now all well-managed disorders. I once tried to calculate the number of lives that have been saved by partial solutions and lives improved based on this kind of work. And I'm absolutely sure it's in the millions. I can't calculate it perfectly, but it's a huge impact. You know, as you all agree, or you wouldn't be here, rare diseases are rare until you start talking to people sitting next to you, and then they're not so rare anymore. So what about the future? The past is wonderful to talk about, but I want to close talking a little bit for a few minutes about the future here. Now, I want to make a little disclosure about myself as only fair. For the last 8 years of my life, I have worked at a company that specializes in starting biotech companies. It's a venture capital firm. So you have to know that because you have to think, well, what kind of self-interest does this guy have? So I just make the open disclosure. They've been probably, I loved being a physician. I loved working with patients. I loved being in the ER when I was young, all that stuff. But in terms of impact on patient lives, I probably have had a much bigger impact in the last 8 years than at any other time in my life, even though I don't do patient care anymore. I see hope everywhere I look, not just at the companies that we start, but across the field. I can remember, I've been very involved with gene therapy over the last 10 years. I can remember when I did not believe it was possible and that the risks were too great to use gene therapy on children. I no longer believe that. I am absolutely convinced that we can develop gene therapy for certain diseases in an effective manner. It's not going to be a solution to everything, but it's going to be a solution. Just give you one example, I was recently involved in starting a company called Voyager, not asking you to buy stock, just telling you a story. Voyager is taking the audacious effort to take a disorder called Friedreich ataxia that some of you know, and use gene therapy aimed at the dorsal root ganglia in the spinal column, where most of the problem is, to see if it can improve the production of a protein called frataxin, the lack of which leads to the loss of mobility. Maybe years, but prior to that, most efforts in Friedreich ataxia have been to alleviate symptoms. I don't want to be in the business of alleviating symptoms. I want to be in the business of curing diseases. There is a huge difference. Thank you. Thank you. Thank you. And the other thing I want to talk about is tools. Probably the reason I am most hopeful There's two reasons why I'm hopeful. The amazing explosion and powerful growth of groups of patients that can make a difference in thinking about how dollars are spent. You guys and people like you across the country are making a difference. I start companies all the time. I've started 7 companies with others, of course, in the last decade. And first on my list, and I am not kidding you, is go engage with the patient groups. Learn from them, get their trust. They often teach me way more about the disorders than I see in the medical literature. It can inform clinical trial design and endpoints. You guys are making, and people like you are making a huge difference. And then on a more technical note, the tools. The ability, the mind-blowing ability now at low cost to sequence the human genome. I can remember when I was a young medical student talking to my mentor. I'd like to mention her name, long departed, Dr. Marjorie Shaw, who introduced me to the world of genetics. And we would walk down the streets of Houston together, and we'd say, can you ever imagine that we might be able to read the letters of the DNA code? No, not possible. But now, for $1,000 or so, you can get your exome sequenced. We still have a lot to learn about what the information means. You've heard about induced pluripotential stem cells. I can tell you, in two companies I'm working on right now, iPS cells taken from patients, skin biopsy from patient, create an iPS cell, grow it up, it becomes a new way of screening drugs with a much more, I think, ultimately powerful readout to help us think what kind of molecule should we try to develop. And oddly enough, computational biology. The amount of data in the biotechnology world that is now being generated is just so vast that we need new tools. And I'm not a mathematician, I certainly can't tell you about them, but we have people that now have the ability to take billions and billions of bits of information, run them against a stratified group of patients and ask, what does it tell us? Do we have a new angle here? The latest thing I'm working on personally is a company that's trying to understand the genetics of a number of kidney diseases. And core to our work is going to be creating large data. Our aim is to create the largest patient registry that has ever existed for renal diseases. Sequence everybody and ask, what is the road to proteinuria? Some of you know that's a very common road to kidney failure, to be spilling protein in urine. But it's not one disease. Hidden within end-stage renal disease is many probably monogenic disorders that we're going to figure out. So I hope that what I've done, well, I've certainly kept you in the room, which I'm pretty happy about, because there's probably drinks out there somewhere that you're ready for. I hope that you will stay with me and be in a partnership with each other for the rest of your lives. And every year, I guarantee you, you're going to hear good news. I mean, two days ago, first approved drug for Duchenne muscular dystrophy. It's not a home run, but it's approved. It's going to help some kids. So, do we have time for any questions? So, I'm happy. I hope you're happy. So, anybody want to make a comment or ask a question? We got a few minutes. Or if you don't, that's cool too. That lady there. I think someone's bringing a mic.
Just when you have free time, if you ever do, what do you do to relax? Because you're amazing.
Well, I wonder if my wife Nancy is in the room. I don't see her. There she is. By the way, I want you to know Nancy, who's been a wonderful friend and companion to me for a very long time. And she would... And I won't ask her to speak, but she would probably say to you, it's really good that he stays busy, because around the house he screws up everything. It's probably... Is that about right, dear? Yeah. I'm always losing things, and I'm not allowed to do much because I do it badly. So thank you for asking, but I happen to love to write, so that just keeps me out of trouble. Yes, ma'am. So that was a very nice question. The lady asked, can we say a few words about genetic deletion syndromes? Now, that's a broad class of relatively poorly understood disorders. A lot of it depends on the size of the deletion. A very big deletion may often be incompatible with life, because when you say a genetic deletion, you're really saying a measurable, if you will, I'm being simple-minded here, a measurable group of genes missing from some chromosome. And if it's big enough, it can either be very severe or even incompatible with life. We have tools, this is a somewhat tangential answer, but we have tools now that allow us to look for many much smaller copy number variations, either deletions or duplications, that are actually quite common, and those may give us insight into forms of developmental disability that we don't currently understand. But I bet you're asking from a therapeutics point of view. But one of the things that's always challenging when you talk to a committed audience like this is to be realistic about hope. The current technologies to try and help people with deletion syndrome still have a long way to go, I think, honestly. You can, usually the good news though is that for some deletion syndromes, even though there might be 6 genes missing, say I'm making this up, it may be that actually the body can tolerate losing 4 or 5 of them. And if you could figure out which one is the most, we call this the critical region. If you could figure out how narrow is the critical region, maybe you could make a difference using some of the more conventional therapies I've talked about. Those are among the toughest things to work on, honestly.
Thank you very much for talking to us all today. Really appreciate it. During your talk, you used the term MR quite a bit, as opposed to intellectual disability.
Yeah.
And I wanted to ask you why you
Oh,
do that.
sure. I'm glad you brought that up. I was talking about the past, and during those years, MR was the word that was used, and it was used without a sense of stigmatization. For example, the president's sister, Eunice Kennedy Shriver, naming the institution where I became the executive director, named it the Eunice Kennedy Shriver Center for Mental Retardation. I totally am comfortable with changing the cognitive disability, developmental delay. I was reflecting the history of the time. Okay? But it's good to, always good to bring up the language.
Just more of a statement than a question. I loved your presentation. I'm a nurse. I've been a nurse for 20 years.
Keep
and so
talking.
the history that you gave was a great lesson. And just to reiterate what you just said, earlier in my career, I worked with children at a facility, and it was referred to as mental retardation. And so I think we've come a long way, and I think organizations like Global Genes and everybody sitting in this room is going to help to improve, and it comes back to the education and awareness. So thank you.
Good point.
What are we doing on the study of Alzheimer's disease? Anything, hopefully, in the future?
Big question. I'll try and address it for you. So, as you know, there is a vast amount of research going on Alzheimer's disease. Alzheimer's disease was described for the first time in 1906 by an Austrian physician. And there was almost nothing done about the disorder for the next 40 years. The main reason being that nobody was really living long enough to get it. Cancer was taking out everybody. So it's really post-World War II that we started working on it. So we know some interesting facts about the genetics of Alzheimer's. Very, very simply, we know of 3 or 4 single gene forms of it that are very rare, but they may teach us about it. I call them the presenilin genes. That represents maybe 1% of all Alzheimer's, and it's usually early onset. Then there's I don't know how many people in this room have heard about a protein called ApoE, but it turns out that there's a common variant of ApoE called ApoE4. 2% of the people in this room have 2 copies of ApoE4. That's a lot, 2% of you, 8 or 10 people. That, statistically, very good numbers, increases the risk of Alzheimer's disease manyfold and earlier age of onset. Now, The major problem in Alzheimer's, and I'm not an expert, I'm just trying to do the best I can here since you put me on the spot, right? So the main problem in Alzheimer's is, one, we don't really understand the correlation between what we see in the neurohistology, the plaques and tangles, and whether those are a consequence of Alzheimer's or a cause of it. I think most people in the field think it's a cause now. So I was talking about this when we were talking just the other day at my firm about starting a company around this. The idea is, can you give a molecule that will pull these inappropriate placed aggregates of condensed protein, tau and amyloid, out of the brain? And when would you have to do it? One of the things we don't talk about enough in meetings like this is, what is the real treatment window? You know, to treat a brain that's already loaded with these plaques and tangles may be very difficult. But I mean, I have colleagues who are real experts in this disorder. They are quite hopeful. I think the key thing is finding people well before, people who are really at risk and treating them early. I think that's going to be true for a lot of the neurodegenerative disorders, ALS, Parkinson's disease. By the time people are diagnosed, I fear that it might be too late for many of them. But huge research going on, a lot of optimism. Many billions being spent on it, both in NIH and in the private sector. Lady in the back.
With the statement you just completed, it sounds as though there's not hope for PVL, paraventricular leukomalacia.
I'm sorry, I'm having a little trouble here.
With the statement you just made, it sounds like there is not hope or much hope for the cure for paraventricular leukomalacia.
Well, it would be very much a contradiction for me to say that there's no hope, because I've given you a message of hope. One, let me be open. I don't know the disorder well enough to comment. By the very name of it, I can imagine what's going on there. But no, I'm not going to say there's no hope for that. I just don't know how much hope there is yet. Hopefully you and I can work together and make the hope a little bigger. Oh no, this gentleman here in the blue shirt. Okay, these two are the last questions.
You mentioned research into renal failure. What do you think of the concept of the artificial kidney?
I didn't hear the last part.
What do you think of the concept of the artificial kidney?
Well, I love the concept. You got to be careful now. I might go on a rant about kidney disease. I am ashamed of our failure with kidney disease. The last two major advances in kidney disease occurred in the 1950s. And this is true because I'm working on a kidney disease company right now. There's not been a new drug approved to treat kidney disease for 30 years. So anybody who thinks dialysis is a solution to kidney disease is mistaken. Life expectancy on dialysis is short, and it's a very unpleasant life. People should think of it as just as bad as a severe cancer. You know, in our society, we're very focused on cancer, but there are many other diseases, end-stage heart disease, that are just as bad or worse than many cancers. Transplantation is a solution for about 20,000 people a year in the United States. There are over 5 million people who meet the definition of kidney disease in the United States. It just takes a long time to get there. An artificial kidney, it's not easy. It's a big challenge in biomedical engineering. The kidney filters 180 liters of fluid a day perfectly. It's going to be a long time before we can match what nature has done. But we should be able to improve on dialysis. But here again, a good note to end on is we want to really think a lot about early detection and prevention. And that should be, no matter what disease we're worried about, the earlier you know the problem, the better you can manage it. Well, this lady's going to.
Dr. Reilly, I'm really inspired by your journey from being a doctor to being a venture capitalist. I was wondering, with the energy we have in a community like this, could there be some setup like a microfunding for research for ultra-rare diseases? Because I imagine we all have a small circle of people, and none of us can do it alone, but maybe we can do it together.
Did everyone hear that? Okay, so first of all, it's a great question to end on, and it's a great question, period. Thank you for giving the opportunity to comment about it. I think about this all the time. I mean, I exist in a world where large institutions, usually universities, put money at our disposal to create companies. They want a return, right, on their investment. That's the society we live in. Especially for the disorders that you care about, the ultra-rare disorders, we are in desperate need of new models, new regulatory models, new clinical trial models, new funding models. One thing I've thought about, and I've talked, there's a group some of you may know called Biopontus that's thinking about this. One thing I've thought about this is, could you start a company? Bear with me, it's a little bit complicated. Could you start a company that's, on paper, a for-profit company? And what it is it's a single umbrella with one CEO, one administrative group, but within it, 20 different silos, each one a different disease, rare. And each one is a partnership between a patient foundation that's maybe putting up, not huge sums of money, maybe several $1 million, and a venture group that's pairing it with appropriate rewards flowing back, so the patient foundation makes money on the deal too to fund further work. And of course, Vertex and the Cystic Fibrosis Foundation are the great example of this. We need to do that. The hard fact is among the thousands of genetic disorders, there are many that are so rare they will never inspire companies to go after them. So we have to do that for those patients. And it's just what you said, community, and I totally believe there are economic or financial structures to accomplish that. And I don't even think it should be that difficult. So you've been a great audience. I was told I weren't going to get too many people, but I'm really very happy. And go out and have your reception and have fun tonight. Thank you.